Now we are beginning part 4 of NPRE 451, and this part is on scintillators. So here are our two key concepts for Chapter 8. Organic scintillators. Scintillation light comes from the de-excitation of the excited molecules. Those molecules could be in any state, solid, liquid, or gas. Number 2, inorganic scintillators, scintillation light comes from the de-excitation of the crystal lattice. Since the crystal structure is important, these must be solid and grown in ways to keep particular energy states of the lattice. Before we really get into this, I just want to remind you of the block diagram that we have for the scintillators. So you recall that we have our scintillating material right here, and then we have the photocathode here, whose job is to convert light to charge. Then we have the photomultiplier tube, or a photodiode, and this is what amplifies that charge. Then this is going to be output into some sort of shaping amplifier like we've already described, and into our multi-channel analyzer, and this is where the spectrum comes from. So anything that is to the left of this line is Chapter 8. Chapter 8 is where we talk about the scintillator itself. Chapter 9 is where we talk about the photocathode and photomultiplier tube. The shaping amplifier and MCA we discussed in chapters 17 and 18, and then we have the spectrum here, which is what we talk about in chapter 10. So let's get into a couple equations that describe scintillators. First off, we have what's called the light yield. And light yield is the differential of light with respect to path length. So this is light yield. And the light yield can be related to the stopping power of our scintillator. So we're going to have some constant S here, which is going to be our scintillation efficiency. How good are we at making light, times the stopping power, dE dx. Now this scintillation efficiency, S, is going to equal the number of photons created, and that is multiplied by the light yield, or energy per photon. Okay, and then that is all divided by the total energy deposited. Total energy deposited. Lastly, we know that scintillators, when energy is deposited and they scintillate, that scintillation light intensity is an exponential, so it drops off with time. So if I describe the intensity of the scintillation light as a function of time, I of t, this is just a normal exponential relationship that we're used to. So this is I naught, that's our initial brightness of the light, times e to the minus t divided by tau, where tau is the decay time of the scintillation light. Now we're into the photomultiplier tubes and photodiodes. So this is the thing that's going to measure the light coming out of the scintillator. PMTs take scintillation light and convert it to electrons at the photocathode. Those electrons, typically a few hundred, are multiplied through the dynode structure of the PMT to result in charge pulses on the order of 10 to the 7 to 10 to the 10th electrons, while also preserving the timing information. Number 2, photodiodes are based on semiconductor principles where the light is converted to electron-hole pairs that are either directly counted or multiplied and counted. So there are a few terms that we use to describe our PMTs. First off, we had this thing called quantum efficiency. And quantum efficiency is the number of photoelectrons, I'm just going to abbreviate that as photo-E's, emitted per incident photon. Okay, so per incident photon. All right, and we want that number to be large. The second one is we have this thing called little delta, and that is the multiplication of a single dynode. And this is the number of secondary electrons emitted per incident primary neutron. Or incident primary electron, my bad. Primary electron. Okay, and then we had G, which is the overall gain of the PMT. And this was equal to some constant alpha. Alpha is the fraction of all photoelectrons collected by the multiplier structure, which for all practical purposes is around 1. And then we had our single dynode gain, and then we raise that to the power of n, where n is the number of dynode stages within our photomultiplier tube. Lastly, we look at our total output voltage of our scintillator photomultiplier tube combo. And this is our usual Q divided by C, which you've seen many times before. This is going to equal the energy deposited times the scintillation efficiency times the light collection efficiency. So that's how much of the light that's created in my scintillator can I actually collect, times the quantum efficiency, times the overall gain, and then because this is in terms of charge, we have to multiply with this by the charge of the electron, 1.6 times 10 to the negative 19th coulombs, and this is all divided by C, which is my capacitance of my photomultiplier tube. Here we are now concluding our part 4 on chapter 10, radiation spectroscopy with scintillators. This first key concept here could almost be the second overall key concept for the course. Any peak in a spectrum exists due to full energy deposition within the shaping time, but it doesn't have to happen in a single interaction. Number 2, the 3 major gamma ray interactions all result in unique spectral features, but do not all originate from full energy deposition. So obviously the type of interaction and its probability is going to be important here for our discussion about spectroscopy. So let's start with what's the probability for the photoelectric effect. So this is sigma sub PE. This is the probability of photoelectric effect. And you remember that this is proportional to the atomic number of the absorber to the 4.5 divided by the energy of the gamma ray to the 3.5 power. So this is why it is important to have high atomic numbers for our scintillators if we're wanting to detect gamma rays through the photoelectric effect, so through peaks. If we want to do spectroscopy, we want peaks, and peaks means that we have to have high atomic number. Okay, the photoelectric effect, you remember that the energy involved, let's see, E is equal to h nu, that's the energy of the gamma ray, and then this is minus the binding energy of the electron liberated, and that's typically small, so this is actually just approximately h nu. Compton scatter, on the other hand, remember we have a scattered gamma ray of a new energy, and this is equal to the energy of the old gamma ray divided by 1 plus that energy of the old gamma ray divided by m naught c squared times 1 minus cosine theta, where theta was my scatter angle. And we also had, when theta equals pi, we have the backscatter peak, and this occurred at the Compton edge, E sub c. So the Compton edge is located at E, the original energy minus E at theta is equal to pi. Okay, and then there was pair production. In pair production, we had the energy of the electron plus the energy of the positron, and that was equal to h nu, my gamma ray energy, minus 2 m naught c squared, or 1.022 MeV.